Chapter 16, Quantum Rotation. Section 16.1, Classical Rigid Rotors. The simplest rigid rotor is a one-body, two-dimensional rotor, which is a particle rotating in a perfect circle with a constant radius. R0 denotes a constant radius. The kinetic energy of this particle is the rotational energy of the particle. Kinetic energy is half mv squared, and we have a circular motion, so the speed is d r0 theta over dt. R0 is the constant radius. Therefore, the kinetic energy is equal to half m r0 squared, and now d theta over dt squared. mr0 squared is the moment of inertia of this rotating particle, denoted by I. d theta over dt is the angular speed of the rotating particle, denoted by a Greek letter omega. The SI units of I and omega are kilogram meter squared and second to the power of -1, respectively. This theta is in radian, not in degrees. So if a particle finishes the motion of this entire cycle within 1 second, then d theta over dt is 2 pi per second, assuming a constant speed. The angular momentum vector of the rotating particle is the cross product of the radius vector r and the momentum vector of the rotating particle. So L is r cross product p. L is the angular momentum, r is the radius vector, and p is the momentum vector. In a perfect circular motion, r and p are always perpendicular to each other. In this case, this L is simply r cross product p. Its magnitude is simply r times p. This r is the magnitude of the radius, and this p is the magnitude of the momentum. The kinetic energy can be written as 1 over m times mv squared, and this means the kinetic energy can be written as p squared over 2m, or in this case, with a perfect circular motion, it's 1 over 2m r squared, and then we have r cross product p squared. So we can also rewrite the expression of the kinetic energy of a rotating particle in a perfect circle. It's 1 over 2m r squared multiplied by the angular momentum squared, and therefore it's L squared over 2I. L is the magnitude of the angular momentum, and I is the moment of inertia. A rigid rotor has a constant radius and a constant moment of inertia. The simplest rigid rotor is a one-body, two-dimensional rotor, which is a particle rotating in a circle. The kinetic energy can be written as L squared over 2I. L is the magnitude of the angular momentum, and I is the moment of inertia. R0 here is a constant radius. Omega is the angular speed. Omega is d theta over dt, and L is I times omega. L is the magnitude of the angular momentum. More generally, the three-dimensional angular momentum can be written this way. The L vector is the r vector cross product the p vector. The p vector is m times the v vector. So L vector can be also written as the mass multiplied by the cross product of the r vector and v vector. We can also express the angular momentum vector as a determinant. Well, this is just because the cross product of two vectors can always be written in this form. Ij and k are the unit vectors in the x, y, and z directions. X, y, and z are the three components of the r vector. Px, py, and pz are the three components of the p vector. We can decompose a 3x3 determinant systematically into three 2x2 determinants like this. So we have these x component, y component, and z component. After the expansion of those 2x2 determinants, we have the expression of the vector of the angular momentum over here. So for example, the x component of the angular momentum is y times pz minus z times py. Over here, this is just a particle rotating in a perfect circle, and you can see the angular momentum L is the r vector cross product the p vector. Tau is the torque. The torque is the r vector cross product the force vector. For a classical two-body, two-dimensional rigid rotation, the derivation of the rotational energy is similar. But there are two particles. Therefore, the total kinetic energy is 1/2 m1 v1 squared plus 1/2 of mv2 v2 squared. m1, m2 are the masses of the two particles. v1 and v2 are the speed of the two particles. Note that m1 r1 should be equal to m2 r2 for a two-body, two-dimensional rigid rotation, assuming there's no any other motion. R1 and R2 are the distances from M1 and M2 to the center of the mass. Alright, so over here this is R1, over here this is R2. The C denotes the center of the mass of the entire system. If M2 is heavier than M1, C should be closer to M2. The two masses have the same angular speed, so when they rotate, they travel at the same angular speed, but not necessarily the same speed, because R1 and R2 are often different. The speeds of the two particles are V1 equals R1 times d theta over dt. V2 is R2 times d theta over dt. Therefore, we can rewrite the expression of the kinetic energy as this: 1/2 multiplied by m1 r1 squared plus m2 r2 squared multiplied by this angular speed squared. This expression can also be simplified to 1/2 times I times omega squared. Omega is the angular speed, d theta over dt. I is the moment of inertia for the two-body rotor or two-particle rotor. I is simply m1 r1 squared plus m2 r2 squared. The two-body, two-dimensional rigid rotational energy can also be expressed as this. It's P1 squared over 2m1 plus P2 squared over 2m2. Since we have m1 times r1 equals m2 times r2, so m1 times r1 equals m2 times r2, and therefore m1 v1 is equal to m2 v2 for a rigid rotor. Well, because v1 is simply r1 times d theta over dt, v2 is r2 times d theta over dt. v1 and v2 are the speeds of m1 and m2. And now we set P is equal to m1 v1 and P equals m2 v2. Now we can further simplify the expression of the kinetic energy of the two particles. We'll just combine these two because they have a constant, this p squared in common. So the kinetic energy is 1/2 times the sum of 1 over m1 and 1 over m2 multiplied by p squared. Again, it's just because this p1 is equal to p2. Now we have this expression 1 over 2 mu times p squared. Here 1 over mu is defined to be 1 over m1 plus 1 over m2. Mu is called the reduced mass of the two-body system. If we take the reciprocal of both sides, mu is m1 times m2 over m1 plus m2. And now we have this expression of kinetic energy of this two-body, two-dimensional rigid rotor. It's p squared over 2 mu, or it can be written as this: 1 over 2 mu r squared, and then here we have the angular momentum squared. Therefore, again, the kinetic energy is L squared over 2I. L is the magnitude of the angular momentum, and I is mu r squared, and mu is the reduced mass. I is the moment of inertia of the two-body system. We can prove this mu times r1 plus r2 squared is equal to m1 r1 squared plus m2 r2 squared. Now let's prove this. Let's prove mu times r1 plus r2 squared is equal to m1 r1 squared plus m2 r2 squared. 1 over mu is equal to 1 over m1 plus 1 over m2. Again, these two expressions are both the moment of inertia of this two-body, two-dimensional rotating system. Again, m1 r1 equals m2 r2. Therefore, the ratio between r1 and r2 is the ratio between 1 over m1 and 1 over m2. And now we have a ratio among three terms: r1 plus r2 versus r1 versus r2 is 1 over mu versus 1 over m1 versus 1 over m2. Therefore, r1 is r1 plus r2 times mu over m1. r2 is r1 plus r2 times mu over m2. Now we're derive m1 r1 squared plus m2 r2 squared. Well, we'll just replace r1 with this: r1 plus r2 times mu over m1. We will replace r2 with this: r1 plus r2 times mu over m2. Now we expand both terms like this. There is definitely a common factor, which is r1 plus r2 squared. We can see that here. We can see that here. And also we see mu squared on top, mu squared on top. Therefore, the common factor is mu squared times R1 plus R2 squared. And on the left hand side, we have M1 over M1 squared. That's the reciprocal of M1. In the second term, we have the reciprocal of M2. Yeah, we look at this, the sum is 1 over mu, so we have this here. The result is mu times R1 plus R2 squared. So we just proved the moment of inertia can be written as m1 r1 squared plus m2 r2 squared. It can also be written as mu times r1 plus r2 squared. The moment of inertia of the two-body rigid rotor can be written in both ways. Its kinetic energy is just the angular momentum squared over 2I. Now let's imagine this is a diatomic molecule. So given the mass of the two atoms, we can compute mu. Given the bond distance, we have this R1 plus R2.